We're going to review, and then we're going to talk about eccentric connections. Hey, so I know you probably haven't been staying up every night late thinking about this. You've been working on your homework, right? But what forces and stresses do we have to elastically account for in the following connection? What do we have? Is this an eccentric connection, first of all? How do we know?
Force is actually offset from the middle of the connection.
That's right. The force is offset from the center of stiffness. From the center of stiffness of the connection. There is, in a sense, a eccentricity. Right? Right? So I got another question for you. Oh, man. Okay. There it is. Another question for you. What if I changed my connection? Instead of looking like this, what if it looked like this? I have a plate. I have that same connection, and there's a weld right here. And I loaded it like this. Is that an eccentric connection? So if I drew another view of it, it would be, my eye was here looking at it. It would be a plate, the centerpiece with the load on it. Is that an eccentric connection? Yes. It's a 50-50 chance, right? Yes. The answer is yes. How did you know? Brilliant ones. Exactly. It's the same criteria, right? The center of stiffness for the connection is here, right? The load is here, right? There's an eccentricity. Yes, this is an eccentric connection. Don't worry, we haven't learned how to do this yet. That's today's lecture. Woohoo! Okay. We've been talking about these type eccentric connections. So I'm going to go back to my original question. What stresses do we see, or forces do we see on a connection like this? Remember, there were two of them. What were they? Torsional, right? Torsional, and they had stresses that looked something like that, right? They spun around the center of stiffness. Yeah? What other stresses do we have? Shear. That's right. Shear. And they all are going to look like this, aren't they? Right? Now, please realize that every one of these forces are acting right on that bolt, right? And we're going to have a component that goes in this direction, another component that goes in this direction, and we got to find the resultant. Remember that from physics? Yeah. Okay, we're not going to do that. We've done that in the past several times, but it's just good to refresh and bring ourselves back up to being on the same place. And those resultants are what we designed for, right? Right? Okay, so can we use these resultants directly for design? Yes. Yes, we can. And that's called an elastic design. And I say, hey, where is the center of twist? Where's the center of twist? Remember, for elastic. Remember that? Where's the center of twist going to be for a connection like this? Does anyone remember? What is the center of twist? What does that mean? Who is a bolt? Okay, so you both need to remember. You were right over there, and I started pulling on you. Where did we rotate about? Where was the point of rotation? Who remembers? Yeah, it's where a line perpendicular to all the resultant forces come together. That's exactly right. That is the answer. Where was it over there? It was in the wall, right? What? In the wall? It wasn't even on the cardboard? No. No, it wasn't. The center of twist, which we call the elastic center, was like out here, and it was exactly what Jennifer said. There's a resultant from each one of these forces, and if we drew a line perpendicular to those resultants, all of those lines would go through one point, and that point would be the elastic center. Right? Coming back. Great. So she nailed it. Where's the center twist elastically? Oh man, it's the single point that's perpendicular to the resultant from every one of the elastic loadings. That's where the center of the elastic or the center twist is, the elastic center. Say, how do all these things change for inelastic behavior? Or what did we assume under all this? We assumed perfectly elastic. What does perfectly elastic mean? What does that mean on a stress-strain diagram if you're perfectly elastic? Nothing is yielding. That's right. If you're perfectly elastic on the stress-strain diagram, that means you're here. Right? And do you remember I was talking about why that'd be really sad to limit yourself to that? Remember why? Because if we call this epsilon y, how far do we get to go before it fractures or breaks? Who remembers? What's that? Well, through the yield plateau, then through the strain hardening, and there's this point. And how much further is this point than epsilon y? 15% is here. That's right, though. Good answer. 15% increase in strength. What is the increase in strain? 88 times. 88 times. This is 88 epsilon y. That's why limiting yourself to only one bolt being engaged, or limiting yourself to when yield just very starts to happen, is highly cautious. Because look at all this play we got in here. You with me? So it is a little silly to use elastic-based design, but we can. It's possible, it's conservative, and sometimes it's the only answer. Okay? But a lot of times it's not. A lot of times it's not. So how do these things change for inelastic behavior? Yep, David, you're right. We're no longer on this very first linear portion of the diagram. Right? We're going to have to venture out here. Okay? What other things do we allow to happen? So we allow this type of yielding to happen in the bolts? Yeah. In the plates? Yeah. What else do we allow to happen? Anything? Slippage. That's right. Slippage in the plates is also allowed to happen and occur. Not a big deal. It just moves a little bit. So is it okay to allow inelastic behavior in connections? Yeah. Yeah. I don't know how many times I'm going to have to smack on you before I get you to say yes to that if you're a little nervous about that. Okay, but it all comes down to this diagram. It all comes down to that. And it all comes down to understanding structural resiliency, right? That's what it all comes down to. So how do we design inelastic connections? Chart. That's always a good answer. And that's right. That's right. Let's say we didn't have a chart. Who remembers? We never worked a problem, so I don't know if I expect you to remember this right off the top of your head. But if you remember what changes from the elastic center to the inelastic center, do you remember? It's going to move, right? Because things are going to yield, right? So these resultants are going to get longer and longer, and they're going to move and rotate. And, ooh, they're gonna all pack in real nicely, right? And so the instantaneous center is actually going to be moved as we start to yield, much like the neutral axis moves between the elastic neutral axis and the plastic neutral axis. And I hope that's not the first time you've heard that. I know for the large majority of you it's not. Okay? It moves. Things give. And that's okay. All right? So the elastic center is going to move to this point that we call the IC. What's IC stand for? Instantaneous center. The instantaneous center. And what's that mean? That is the point of twist right before failure, right? Right before failure. Where's the instantaneous center going to be at? That's what we don't know. Believe it or not, to find it out, if you don't have those charts in the book, if you're dealing with something that's odd or strange or hard to deal with, you actually have to guess an instantaneous center. Okay? And then you have to look at the moments applied externally, and then you have to look at the moments applied internally. They have to balance. Where you're assuming every one of these bolts are at their limit. Okay? So if you assume every bolt's at their limit and you assume an instantaneous center, now you know the orientation for each one of the force vectors on the bolts. They have to be perpendicular to the instantaneous center, right? So you solve that internal moments have to be equal to external moments. You're with me? So what happens if you find out they're not? What do? Guess a new one, right? Exactly right. You guess a new one. Keep guessing until they match. And you can write a spreadsheet to do that. Okay, it's very good use, the spreadsheet to do something like that. Okay, but we've got the manual, right? So we don't need spreadsheets, at least not for a lot of this stuff. But it's not that hard to write a spreadsheet. And this class is not about writing spreadsheets. This class is about understanding behavior, understanding how things work. And when you can go off, you can write all the spreadsheets you want on your own time out of the class, all right? But we've got a lot to learn. We've got a whole lot to learn in this class. So how do we design inelastic connections? We just talked about that, right? You guess an instantaneous center, check the external moments versus the internal moments, find out where they balance, or the probably more appropriate answer is use the chart, right? Use the chart in the book. Awesome. So we were working problems last time. Oh, yeah. This is also really important. This is really, really important, and we're not going to talk a lot about it, but this is totally fair game for a test problem. Okay? This chart about what are the differences, what's assumed under elastic and inelastic, right? What's important. And I don't mind telling you that because I want you to learn it, and that's what tests are about. Getting you to learn, right? Getting you to know these things. Okay? So you think I'm going to ask you this chart? Please regurgitate the chart on the test. Hell no. Okay? But I will definitely ask you concept questions and ideas and things that blatantly refer to this chart. It's about knowing, not about regurgitating. All right? Okay. We were working an example problem last time. And if you recall, was on table about 738, and that was on the 13th edition. So now I'm looking in the 14th edition. So in this table, if you recall, there's things like coefficients for eccentrically loaded bolt groups. You've got an angle that's in here. You've got some information about the number of bolts in a row, the spacing between the bolts, all these things, and you plug into this table, and what do you get out? Don't just tell me a number. What does that number mean? What does it mean? What do we get out?
Number of equivalent bolts.
That's right. The number of equivalent bolts. That means we may think that we're starting out with 2 rows of 12 bolts. So that'd be 24, right? But as our eccentricity goes up and up and up and up and up and up, we don't really have the same equivalent as 24 bolts. We only have the equivalent of, go away, of 14. 14 bolts. 14 bolts in shear. Or 14 bolts in bearing or tearing, whichever one controls. We'll finish that out today. Talking about that today. It's the capacity of 14 volts, 14.2 volts. Okay? So that's what we get. Awesome. So we worked this problem together. It's part of it. We came in with an eccentricity, 4.5, and I got that from my diagram. My vertical spacing was S. My number of volts was 3. I went into the table and I found, oh no, there's no 4.5 under an eccentricity. It's not there. What do? Give up? Yes. Can't do it. Not good enough. No. You could, but would you use 4 or would you use 5? You'd use the conservative answer, right? You'd use the one that requires more. You could do that. Or you can interpolate, right? You can interpolate for the eccentricity. You can interpolate for the bolt spacing. I don't know how you could interpolate for the number of volts, though. That would be tough, right? 3.5 volts. Okay, I don't think that was going to work, right? But how about the angle? Can you interpolate on that? Absolutely, positively no. So what do? Be conservative. You look between the two angles. You work the problem twice. Oh no, how sad. You have to work the problem twice for 2 different angles. You figure out which one gives you the more conservative answer, and that's the one you use. Yeah? If you don't like that, make your own spreadsheet. Okay? Okay. But I'm expecting you to turn in the conservative answer. Okay, so we did that. We used interpolation. We found 2.83. I said, therefore, the connection has an equivalent strength of 2.83 concentrically loaded bolts. So now we're going to start finding capacities. Okay, so I start out here and I say, well, they're 3/4 inch diameter bolts. And I have 2 strengths down here. Why do I have 2 strengths? Different manuals. 13th edition reports 15.9, and mysteriously, all the bolts have gotten stronger. Well, they've changed the safety factors on bolts. Remember, there is a continuous war between all industries to shave out as much safety factor as possible so they can sell more, right? Because the bolt people are fighting the weld people, right? So if they're able to shave out some safety factor, they're going to be more competitive with welds. That's what happened between the 13th and 14th edition. Now, they may tell a story differently. They may say that, oh, we re-examined the safety factors provided by our past tests, and I'm not saying that's wrong, okay? But they've convinced people that their bolts are stronger, okay? That's what they did. 17.9. Okay, so we're not done. We have to do bearing and tearing calculations, okay? And in our bearing tearing calculation, what's the first term we use? What do we do? What's the first step on bearing and tearing? Compare the bolt diameter to L sub C. L sub C. So what L sub C am I going to use? 3. Now, it's not 3, remember, because L sub C is the spacing between the edge of the bolt and the end, right? But I like your concept and your idea about, well, they're all about the same. But they're not, though. If you look here, you're actually going to have a smaller L sub C here, aren't you, than you will on the edge. And you'd say, but that's only one bolt. What do you mean? This one's not going to have the same constriction. Well, we're going to be conservative right now, right? And we're going to pick the one that's the minimum L sub C, because technically you could do a bearing and tearing calc for each line, okay? You could come up with a capacity for each line. But let's be honest. We just lumped in. We've already done some lumping here. We turned 6 into 2.83. Okay? I'm not so comfortable with going back and doing some like weighted average on what the bearing and tearing capacity is per bolt. You know what I mean? I think it's just time to be conservative. Yes? Remember, L sub C is this spacing here, right? Or this spacing here. right? Or this spacing here, right? So really this minimum spacing are on these two bolts. So on 2/3 of the bolts we're talking about, that minimum spacing is going to control. So it's probably okay just to go ahead and use that. You kind of see the rationale I'm going through there, where it's not blatantly clear in the code on what you should use. It actually just tells you, if you go and read it strictly, it just tells you multiply by the capacity of a bolt. But the capacity of the bolt could be controlled by shear, or it could be controlled by bearing and tearing. You have to make that decision. And we're going to do this over and over again, so get used to it. Where the code doesn't tell you what to do. It expects you to be big engineers and figure it out for yourself. Actually, the code shouldn't be written for every detail. That's not its job. It's to give you overall guidance. Does that make sense? Okay. So, we're going to take our L sub C min, which is equal to 3 inches. That's the spacing. And how many bolts am I going to subtract out? 1. There's a half a bolt on here and a half a bolt here, right? 1 whole bolt. We're going to find that that's equal to 2.125 inches. And L sub C is greater than 2 times 3/4 of an inch. So what's going to control? Who remembers? Bearing. Very good. Bearing controls. Now you say phi RN is equal to 0.75 times 2.4 dt times what? What's the last thing? I'm missing something. Fracture strength. Looking for FU. That's right. It's just fun to say out loud. Right? So phi RN is equal to 0.75 times 2.4 times 3/4 of an inch times my thickness. What's my thickness? 3/4 of an inch times 3/4 of an inch times 65 KSI is equal to 65.8 kips. Okay, so we're going to say that these control, don't they? Shear strengths, the shear strengths are going to control, right? So, whenever you're calling out bolt strengths in this class, you better tell me which manual you're using. You better tell me if it's 13th or 14th edition. Okay? Okay, so we're going to take 2.83 and we're going to multiply it by, if you're using the 13th edition, you're going to multiply it by that and you'll get 45 kips. And if you're using the 14th edition, you're going to take 17.9 times 2.83, and you're going to end up getting 50.6 kips. Remember, they're basically the same answer, right? Just the manual has different capacities for bolts. Does that make sense? And I'm not saying one manual is better than another manual. You'd actually look at your building code and see which one that it recognizes. Okay, and that's the one you would use. Yes, sir?
So when you get that equivalent bolt number, that's like that 2.83 bolts are all in one row?
Yes. We're imagining that these 6 bolts are we're transforming this cross section, this connection, to look like 1, 2, 0.83. All loaded like this. That's what we're doing. Maybe I should call them equivalent bolts. It's a good question. That's what it's doing. Isn't that beautiful? That's what you want. You want design methods that are simple and easy. So when you go off in your career, you'll be able to make some. Learn from these. Don't make your design things complicated. Okay? Make it easy and simple to use. Okay? Any questions? Okay. So the design of eccentric welds is even more interesting than bolts. The same concepts that we use for bolts are used, only this time we have to break our welds into 1-inch segments and then iterate. So imagine in the past, if we'd have done this, we would have guessed an instantaneous center and kept going. No, there's actually instantaneous center numbers in your manual. Okay, there's like an E prime or something you can calculate. Okay, and it'll tell you where the instantaneous center is. Okay, which is sometimes helpful for things that are strange because you'll know about what the answer should be, or it should be between these two values. And that's cool and all, and you only have 6 things to iterate over for bolts, right? Well, guess what? For welds, you have inch-long segments. You may have like 200 things you have to iterate over. Okay, if you have 200 inches of weld, okay? If you have 12 inches of weld, you'd have 12 things you have to iterate over. No fun. No fun. The design of eccentric welds is even more interesting. We break everything up into 1-inch segments and then iterate. This is very time-consuming and very tough to do by hand. Actually, almost impossible to do by computer as well. Okay, spreadsheet, very tough. Very, 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 very tough to do. You can do them for general shapes like C's or lines or things like that, but oh man, it starts to get tough. The AIC manual saves the day again, and we get to use some new set of tables, 8-4 to 811, starting on page 866, at least it did in the 13th edition. Let's see what it does in the 14th edition. Hey, same page. Starts here. There's similar type things here. Similar things we're using. I need to probably zoom in a little bit. You look at this picture now. We've got this epsilon. This E is in terms of AL. Okay. And L is your length of your weld. So you're going to solve for the eccentricity in terms of the length. Does that make sense? So if your weld was 10 inches long, and your eccentricity was 1, your A would be 1/10, wouldn't it? 0.1. Okay. Hey. We have A's down here. Oh, you can't see any of that. Then we have these things called K's down here, and these K's are in terms of the... Come on, baby. Come back from... There you go. K's are in terms of the weld spacing. Okay? All in terms of L. So that's how they've solved it. And there's these terms up here in the top that you may use at some point. These are more for design purposes. So if you know what these other terms are and you want to figure out what your minimum length is that you can get away with, or your minimum D, or your minimum C, these are things that are helpful. Okay? Okay, so you're going to ultimately plug into this equation at the top. C times C1 times D times L, and that's how you're going to solve for what your capacity is. And I always forget this every year, and I'm going to look, see, aha. In my opinion, they could make this table a little more useful. Okay? This table is somewhat similar, where you're basically coming up with an equivalent length. This equivalent length of weld. Okay? That you're going to plug into this equation. I think you actually come up with a C factor that transforms your length of weld into an equivalent length. They have this C1 factor that they actually use based on the type of weld, the electrode strength. And it's here on the previous page. It's pretty easy to use. 0.857, 1, 1.03, depends on the electrode strength. Why do you think they're doing this? Well, the entire table is actually solved for in terms of, all the work was done for an E70 electrode. Okay? And then if you go to use a different electrode, you should be able to get more strength out of it, right? Right? But if you notice, this is a change of 10 KSI, right? You'd think you would get like a 1/8 improvement in strength, right? Or a 1/8 improvement in strength. But it only goes up by 3%. What's going on here? Remember, welds are brittle beasts, right? And as you go up and higher in strength, what happens to ductility? It goes down and down and down and down. So it's not just a strength offset here. There's a ductility offset as well. So you may do something like almost double your weld strength, but yet you're not getting double the capacity because of the ductility requirements. Okay? Okay. So let's see if there's anything major that I'm leaving out here. Oh, yeah. Forgot something. So these problems aren't hard. They're really not. They're about looking and getting some of these terms. The C is going to come from our table below. Okay? Table below. The C1 is going to come from the electrode. Right? That's that previous table I showed you. The D, that's the number of 16ths of an inch in the fillet weld side. Hey, it's the same D we're used to using, right? The same D. Right? The L is the length. But guess what? They tell you to use a phi of 0.75, but they don't have it in the equation. It should be there. You need to put a phi of 0.75. Remember when we've done welding stuff in the past, the phi was buried into our constants, right? The phi is not buried into our constants anymore. Okay, it's separate. You have to remember to put it in. Okay? All right. Let's work a problem. I think we can get through this. So it's the same thing. We've done this before, similar type things. You can interpolate between anything you want in the entire table except for what? The angles. That's right. Cannot interpolate between the angles. You're going to choose the one that gives you the more conservative result. Okay, so this is a little bit different. It's the C shape. It's got 4 inches down here, 10 inches up here, and this is another 4 inches. Eccentricity is at 24. This sign means it's a fillet weld with an E70 electrode. And what's this mean? Actually, I think it's in the wrong spot. I think it's actually supposed to be there. What's it mean? It's the leg height, right? It's the leg height of the fillet weld. It's the leg height, and this symbol right here means fillet weld. Okay, so I say it's on table 8, page 890. We'll see if that's still true. Oh, that's always good when that works out. So we're going to use table 8-8 on page 890. That's what it looks like here. So again, we're going to have this A we're going to have to solve for. We're going to have this K that we're going to have to solve for. Okay? Okay? Not that hard. So we're going to start writing some things out. We know the L. The L is 10 inches. It's the length of the weld. But you say, hey, but there's weld down here and here. No, don't worry. It's coming up. Be patient. Okay? The L for this problem is 10 inches. Just look at your picture. 10 inches. Okay? Now we got to find our KL. Our KL is equal to 4 inches. KL. 4 inches. So our K is going to be what? 0.4. So now we need to find epsilon x. So now we need epsilon x, or AL. They're kind of the same thing. Okay, so where do we go from? We go from the load to where? What's that point? They call it center of gravity, which I don't agree with. I call it center of what? Stiffness. Right? Right? I should make you go in there and change every one of those with your own pen, right? Whatever. Center of stiffness. Okay, how do we find it? What's the answer? Is it here? No? Is it about here? How do we find it? Well, you do it just like you find a centroid. Okay? Do it exactly the same way you'd find a centroid. So, now we need it, so we'd say, to get this, we need center of stiffness. So, I'm going to need a y bar and an x bar, right? We can actually treat this just like as if it's a solid, and I want to find the center, the centroid of it. My y bar by inspection is equal to 5 inches, right? If you want to do the math, you can. It's 5 inches by inspection. X bar is summation of A x over summation of A. And we're going to assume that each weld, or I'm going to assume that each weld is 1 unit across. It doesn't really matter what it is. If you want to put in 5/16, you can, but it doesn't really matter because they're all going to cancel. All right? All right? Okay. So I have to say I'm going to have a weld that's 4 inches in length. It's 1 unit wide. I could put 5/16 in there if I wanted to. Okay? And now I have to find the distance. I have to find the distance from, I'll call this my 0 point. I'll call this my origin. That's what I drew in my picture. Okay, just like you would on a centroid. So what's the distance from my origin? That's the center of this weld. So the distance from my origin to the center of this weld. It's 2. Okay. Do I have another one of those? Yes, I do. 4 times 1 times 2. The ping of death is upon us. Right? And then I need to do the same thing for this member. It's 10 inches. I'm going to call it 1 unit long. And what's the distance from my origin to the centroid? 0. Right? Now I just divide by the areas. 4 times 1 plus 4 times 1 plus 10 times 1. Notice all these 1s would cancel, cancel, cancel with cancel, cancel, cancel. Right? So 5/16, 1, who cares? Does that make sense? If you don't like that, use 5/16. No problem. Okay, and you get x bar is equal to 16/18, which is equal to 0.89 inches. So, to find my AL, how do I find my AL? What is AL?
24 minus 16.
That's exactly right. 24 inches minus the distance to my centroid, which is 0.89. I'm going from here all the way to 24 and then back a little bit to find my centroid. You get 23.1 if you do that. So my A is equal to 2.31. So if I go into my table, I have an A and a C. I can have 2.2, 2.3, 2.4, 0.67, 0.623. These are values from the table. These are values from the table. This is what I calculated. So I could have used a conservative one, but I'm going to expect you to interpolate in this class. So interpolated value is 0.647. So what do I do next? Almost there. Plug into the equation. C1. How do I get C1? Table. For an E60 or E70 electrode, it should be 1. What's my D? 5. Very good. What's my L? It's 10. It's 10. Does that make sense? More fun next time. See ya.